Welcome, Algebra 1 students, to Unit 1.2, Applying the Closure Property. You're hearing the voice of Mr. May, and I will be your teacher through this unit. As always, please make sure that you have your guided notes with you. We will be working through those and filling those out throughout the course of this unit. So without further ado, let's go to our learning targets. And as a reminder, please use that pause button and rewind button so that you can have time to write down the blanks for the guided notes and to fully understand the content. Our learning targets, learning target 1.2a, I can explain. There's that verb again, explain. That has a very deep connotation that means that you can go in depth as to your understanding, in this case, of why the sum of two rational numbers is rational. Learning target 1.2b, I can explain why the sum of a rational number and an irrational number is irrational. Thinking back to the previous unit 1.1, both rational and irrational numbers are considered to be in the set of real numbers, but they are two different classifications of numbers. Learning target 1.2c, I can explain why the product, that is a new term, product of two rational numbers is rational. We'll discuss product in the upcoming moments. And then learning target 1.2d, I can explain why the product of a non-zero rational number and irrational number is irrational. Again, we are looking at having a great enough understanding that we can explain the concepts involved in these learning targets. Definitions. This is a review of a definition, this being closure property. The closure property, once again, states that an operation, we talked about operations in the previous unit. Specifically, we are going to be using addition and multiplication as our operations that we can perform on any two numbers from a set. Again, this is the same set of numbers. Going back to our sets, just to list them off one more time. As a review, we have our natural numbers, whole numbers, integers, rational numbers, and then kind of out here by itself, we have our irrational numbers. And then together, all of these numbers compose our set of real numbers. And if we take any number from a set and add or multiply it by another number in that set, we will obtain the result of a number that is also contained in that same set. We used the example in the last unit of choosing the set of integers, adding another integer to that, the result. Once again, we use an equal sign sometimes to represent result. We will get, as a result, a number that is in the set of integers. Once again, the closure property holds for all real numbers for the operations of addition and multiplication. To highlight that subtraction and division are not included inside of this property. Quick review, once again, of classifying real numbers. We did a Venn diagram for an example in Unit 1.1. This is a review of it. The only thing that I really want to highlight from this is two things. The first is notice that the set of rational numbers is separate from the set of irrational numbers, both being contained within the real number set. Second thing that I want to remind you of is that as we began at the smallest set that we discussed being our natural numbers, Natural numbers are also included within the set of whole numbers. Whole numbers just has the addition of 0. Moving outward, integers include also whole numbers and natural numbers, and rational numbers include natural whole integers as well as terminating and repeating decimals. Irrational numbers do not repeat and do not terminate. Using those classifications, we are now going to apply the closure property. We're going to work on the application of that specific property when adding rational numbers. So to go back one slide, the rational numbers, we are focusing our attention on this particular box or set of numbers, everything contained in there. At the moment, we're not going to be working with the rational numbers. So, discussing rational numbers, when two rational numbers are added, remember the closure property holds for addition and multiplication. That's why we really have to highlight added. The resulting sum will assume or will take on the properties of the set of rational numbers. So what we have is if we take a rational number and add it to a rational number, we will get the result of another rational number. So it's going to look like this. We have a rational. We're going to add another rational number to it, and our result will be a rational number. So for example, rational numbers are terminating or repeating. Decimals. So if we were to write a fraction in decimal form and get a terminating or repeating decimal, so let's just say 1.25 plus 2.10, both of those do qualify as terminating decimals. If we were to add those two together, we would end up with 3.35. 3.35 is a terminating decimal, so we have the result of a rational number. So a rational plus a rational, and again, let's highlight our plus because that is added, that will result in a rational number due to the property closure property, which states that if you take any two numbers from a set, the result will be a number that has the properties of that set. So going back one slide once again, so if we take any number from inside of this rational number box, so that also, remember, it includes natural, whole, and integers. If we take any number from inside that and add it to another number inside that box, the red box there that we've highlighted previously, inside again this red box here that I'm going back over, what the closure property says is that so long as we take numbers from that box and add them together, we will get numbers that are contained within that box. You're not going to get a number that is somewhere outside of that box, such as an irrational number. That is what the closure property is saying. And we could take it even further. We could even say that if you go even more refined to a natural number plus a natural number, let's say, for example, 1 plus 3. 1 plus 3, that is equal to 4. 4 is a natural number. It is contained within the set classification of natural numbers. Closure property will hold for all of these sets, but in this case we're dealing with the largest of this red box, that being rational numbers. So example number 1. This highlights learning target number 1.2a. So into what set of real numbers, so again we're looking at real numbers, should the result of adding, highlight that adding, that means that we can apply the closure property. of adding 4.5 and 27/4 be categorized? So into what set could it be categorized? So why don't you hit pause, see if you can work through this example, and then when you come back, I will be working through this. So what is the set classification of 4.5? Well, 4.5 is a decimal, meaning it is either rational or irrational. Irrational numbers either do not terminate or do not repeat. In this case, we see that 4.5 does terminate. That leads us to conclude that 4.5 is a rational number. So what is the set classification of 27/4? Well, notice that 27/4 is not a decimal. It is actually a fraction. But when we look closer at the definition of rational numbers, it says that if you have a number in the form of a divided by b, where a is an integer and b is an integer, then a rational number is a number that when written in decimal form will result in a terminating or repeating decimal. So what we have to do is we have to look, is 27 an integer? Yes. Is 4 an integer? Yes. So we have an integer divided by an integer. So if we convert that to a decimal by taking 27 and dividing it by 4, that is equal to 6.75. Now we can answer the question of what set classification is 27/4. Well, written in decimal form it is 6.75. 6.75 is a terminating decimal. Therefore, we can say that 27/4 is also a rational number. Now, at this point, we're asked the question, what is the resulting sum of 4.5 and 27/4? Well, using a calculator or working it in your head, we have 4.5. Sum means addition, plus 27/4. The answer is 11.25. 11.25 is a terminating decimal. Therefore, we have another rational number. Looking at the last question, what is the set classification of the resulting sum? There's a couple of things. One, we can look at the resulting sum being, in this case, 11.25. The resulting sum is a rational number, which we have already stated in the previous question. But if we were to have skipped all the way down, we were to have looked at the two numbers being added, the 4.5, 4.5, and 27/4, and realized that they're both rational numbers, we could have answered the question, what is the set classification, without even having done the math to get the resulting sum, because we know that because of the closure property, that's the Y, the closure property. Because of the closure property, we know that any two numbers from the same set that are added together will result in a number that is contained within that set. So a rational number added to another rational number will result in another rational number. That is your Y, the closure property, and that it holds for addition. Excuse me. Looking at the next topic, we have applying the closure property when adding a rational and irrational number. Now that's interesting because we no longer have two numbers that are in the same set. So we have a rational and we have an irrational number. Now notice that the closure property says that you're going to get a number that is also contained in the set. Now this becomes a little bit more confusing in the sense you say, okay, well, rational numbers and irrational numbers are not in the same set. So how can we add them? How can we use that property? Well, if you recall, both of these rational and irrational numbers are contained in the larger set of real numbers. So what we're actually doing is we're adding a real number plus a real number, and the result will be a number that assumes the properties contained in that set. Well, what's the set we're working with? We're working with the largest set of real numbers. Now we're going to look specifically at this resulting real number. What properties will it have when we add a rational when we add that rational number to an irrational? So we do know already that a rational number is a real number. We know that an irrational number is also a real number. We know that we're going to get a real number as a result, but what properties will that real number have? In this case, we're going to have a result that has the properties of the set of irrational numbers. So it's going to have the properties of an irrational number. Now let's think about this kind of through an example. If we have 1.25 and we add that to 2.14976831025 and so on forever, will this resulting sum, will this result that is written here, will it ever terminate or repeat? Is there ever an instance where that could occur? And the answer is no, because all of these numbers, they are going to also be contained in the result. Because to add, you may have been taught this in previous math classes, if you needed to add, you could just put zeros forever out here. But when we add all these numbers to 0, you get 5, 2, 0, 1, 3, 8, 6, 7, 9. And now the 5 and the 4 is a 9. 2 and the 1 is a 3. And that is a 3. So what you see is that all of these numbers that continue on and on and on forever are also in the result. And since they're also in the result, we have to conclude that our resulting number is classified as irrational. So looking at this, we can see that both rational and irrational are considered real numbers. The result will be contained in the set of real numbers and have the properties specifically of the irrational numbers. So when a rational number and an irrational number is added, the resulting sum will assume the properties of the set of irrational numbers. Example number 2, highlighting learning target 1.2b. Into what set of real numbers should the result of adding the square root of 17 and 4.0 be categorized? So take a moment and think about how you might approach this example. Hit pause and work through the example And once you've completed, hit play and we'll work through example number 2 together. Okay, looking at the question, it is broken down into 5 different sections, asking about the set classifications of the square root of 17, 4.0, the resulting sum, and then asking why. And so when we think about the set classifications, these are the sets of natural numbers, whole numbers, integers, rational numbers, and irrational numbers. And so when we consider the set classification of the square root of 17, what we need to do is convert that to a decimal. And when we convert the square root of 17 to a decimal, we see that the answer or the result is 4.123105625 and it will continue forever. And so when we think about what the set classification would be, we can immediately determine one of 2 options because of the decimal. And so we either have a rational number or an irrational number. Now, thinking about the definitions of each, a rational number is a decimal that either repeats or terminates. And so looking at the decimal form of the square root of 17, we realize that it does not terminate, it goes on forever, and there is no discernible repetition or repeatable pattern within the decimal. So it does not repeat and it does not terminate. That leads us to an irrational number, which an irrational number in decimal form does not terminate and does not repeat. And so we can conclude that the set classification for the square root of 17 is irrational. Now looking at the set classification of 4.0, once again we have a decimal, and in this case we have a decimal that terminates. And so if I have a decimal that terminates, going back to the definition that I just discussed about rational numbers are decimals that either terminate or repeat. And so we have a terminating decimal, so I can conclude that 4.0 is a rational number. So when we think about the resulting sum, the word sum implies addition. So what we're going to do is we are going to add the square root of 17 and 4.0. And if I were to rewrite these so that they are positioned above each other, above and below, 1, 2, 3, 1, 0, 5, 6, 2, 5, 6, and 4.0, we can immediately tell that these ending decimals, the 2, 3, 1, 0, 5, 6, 2, 5, 6, and I'm going to add the dots just to show that it would continue on forever, however long I wanted to write numbers. They are immediately going to drop down and be a part of the resulting sum. And so without even going any further, we can see that this is going to be a decimal. The resulting sum will be a decimal that goes on forever. It does not terminate and does not repeat. And so we can now conclude, without even finishing the addition, that we are going to have an irrational number. But just for the sake of completing it, we can see that the resulting sum of 8.1231056, 256, and on and on and on and on forever is a decimal that neither repeats nor terminates. And so the resulting sum, so this is our answer for here. And so looking at the last question, or the next to last question about the set classification of the resulting sum, we notice that it is again a decimal that neither repeats nor terminates. And for that reason, we can conclude that we have an irrational number. And so the question is why? Why do we have an irrational number? Well, a couple of things as far as the why is concerned. The first is we can say that the closure property, and let's write closure property applies to addition and the result will be a real number. And so that's point number one. So the closure property applies to addition and the result will be a real number. And if you look at the classifications of irrational and rational, they are not the same set classification. However, both are categorized in the set of real numbers. And so the closure property basically states that any time that you add two numbers from the same set, and in this case, the same set is the set of real numbers, will result in a number from the same set. So adding two real numbers will result in a real number. Now, the next thing is, why is it going to be irrational as opposed to rational? And the reasoning is, let's change the color, the reasoning that this occurs is that since a rational number terminates or repeats, it will assume the properties of the non-terminating, non-repeating set. And in this case, the non-terminating, non-repeating set is an irrational number. Now let's think about it. What we're actually saying with that is if there is not a way, if I look at the example that we've worked, there is not a way to change this portion of the irrational number into a terminating or repeating decimal by adding anything below as a part of the rational number. There is not a repeating pattern or a terminating decimal that we could insert into this yellow highlight that would change the pink highlighted portion of the irrational number into something that would terminate or repeat. And so what this would result in is that those properties that I've highlighted in pink that make this number, the square root of 17, irrational, carry through to the result, making the result an irrational number. And so when you look at the explanation, your explanation is going to be that the closure property will apply to addition And the result of two real numbers, which irrational and rational numbers are both contained within the set of real numbers, will be a real number. However, that real number will assume the properties of the irrational, non-terminating, non-repeating set. Applying the closure property when multiplying rational numbers. Notice that we have now shifted from addition to multiplication. However, if you recall, the closure property holds for both addition and multiplication, meaning that the same conclusions can be made despite the fact that we are multiplying rather than adding. So when two rational numbers are multiplied, the resulting product, I mentioned that we would see the word product again. Product is another way of referencing the operation of multiplication. So just as sum references addition, product references multiplication. So when we multiply two rational numbers, the result will also assume the properties of rational numbers. So writing this identically, or actually not identically, similarly to how we wrote the addition, rational number times a rational number, the result, or equals a rational number. So let's look at our example number 3, highlighting learning target 1.2c. Into what set of real numbers should the result of multiplying 3.2 and 17/4 be categorized? Well, again, we begin with what set classification, or what is the set classification of 3.2? We should now be familiar enough to just realize that it is a terminating decimal and that this would be a rational number. What is the set classification of 17/4? Well, 17/4 is a fraction. We have to convert it to decimal form. In decimal form, 17/4 is 4.25. 4.25 is a terminating decimal, therefore it is a rational number. Skipping once again, finding the result, we can just determine what the set classification of the resulting product referring to the multiplication or the result of the multiplication, the product of a rational number and a rational number. They are both contained in the same set. We can conclude that the result will also be contained in that set of rational numbers, and that is because of the closure property. And to verify, I can find the resulting product of 3.2 and 17/4, and that resulting product is 13.6. Applying the closure property when multiplying rational and irrational numbers. Once again, we're going to see the same pattern as when we added a rational number and an irrational number. So once again, rational numbers and irrational numbers are both included in the set of real numbers. So a real number multiplied by another real number results in a real number. The closure property is holding. If I look at a rational number, so a rational number multiplied by an irrational number the properties of the result are going to be those, and let's write this in green so it stays uniform, will be those of the irrational numbers. And for the same reasoning and logic as that of adding a rational number and irrational number. So if you, again, want to review the logic behind it, you can go back to the slide that highlights adding a rational or an irrational number. Or if you want, you can think about the reasoning behind if I were to choose a rational number. Let's think about 1.25. And I were to multiply that by pi, what would the result look like? And again, think about all of the additional numbers at the end of pi. So it's 3.14 and continues on forever. Think about what those numbers, how they will affect the result when multiplied by a terminating number such as 1.25. Again, the same logic holds with this multiplication as with the addition of a rational and irrational number. Example number 4, highlighting learning target number 1.2D. Into what set of real numbers should the result of multiplying 6.25 and pi be categorized? Consider the question and hit pause and work through the example. And once you've completed, restart the recording and we will work through the example together. So to approach this question, we can break it down into smaller steps, considering each piece individually. And in this case, our individual pieces are our numbers being multiplied. So we have 6.25 and we have pi being multiplied. And then we're also going to have a resulting product. Remember, product implies multiplication. And so to work through this example, we can see that we have to classify each of the individual parts into set classifications. And set classifications of real numbers are natural numbers, whole numbers, integers, rational, and irrational numbers. And so thinking about 6.25, we see that it is a decimal, and decimals are categorized as either rational or irrational numbers. And the definition of a rational number is a decimal or a fraction written in decimal form that either terminates or repeats. And so looking at 6.25, we can quickly conclude that the 0.25, let's clear that off so we can, that the 0.25 terminates. The decimal does not continue. It stops at the 5, the 0.25. It stops. And so because it is a terminating decimal, we can conclude that 0.625 is a rational number. Now, also included in that definition of a rational number is a repeating decimal. And we do know that 0.25 is not a repeating decimal, but a rational number does include both types of decimals. So either a repeating decimal or what we have in this case, a terminating decimal. So that is the set classification of 6.25. Now, the set classification of pi. Well, pi in its current form is not written as a decimal. And so if we were to convert pi into a decimal form, we would see that the decimal form is 3.14,159,265,8,5,8,9,7,9,3, and I could continue on forever. I'm just going to stop there. And so looking at the set classification, again, we can narrow our categories to either rational or irrational numbers. Rational numbers, once again, were either terminating or repeating decimals. And so looking at pi, we know that it is not terminating. It goes on forever. So now we need to determine, does it have a discernible repeating pattern within the decimal portion? So if I were to look at the decimal portion, is there a discernible repeating pattern? And in this case, it does not. There is not a terminating or a repeating pattern. So this is non-terminating, and it is non-repeating. And since it is a non-terminating, non-repeating decimal, our conclusion is that we are working with an irrational number. And so we can classify pi as an irrational number. Now we need to consider the product of 6.25 and pi. As a quick reminder, product implies multiplying or multiplication. And so when 6.25 and pi are multiplied, the resulting product is 19.63493621 and continues forever. And so in this particular case, we can see that once again we have to look at the properties of the decimal portion to determine if we're working with a rational or irrational number. Immediately we can conclude that it is non-terminating, and so we must look to see if there is a discernible pattern within the decimal portion of the number. And once again, there is not a discernible pattern. And so we have another non-terminating, non-repeating number, meaning that the resulting product is once again irrational. And so we can conclude that the product of a rational and irrational number will assume the properties of the irrational number. Now, why is this? Well, the first reason is that the closure property applies to multiplication and results in a number categorized or classified. Let's use classified because that's what the terminology we're working with. Classified in the same set of real numbers. And immediately you may think, wait a minute, rational and irrational numbers are not in the same set of real numbers. And that is true. They are classified differently. However, both rational and irrational numbers are classified as real numbers. They are both in the set of real numbers. So what we're actually doing is multiplying a real number. So we are multiplying a real number times another real number. Okay, so real number times a real number, and actually I'm going to rewrite that to make it a little nicer. Let's do this. Let's do it this way. So we have a real number times a real number. So a real number times a real number will result in another real number. And so the closure property holds for multiplication and results in a real number. Now, what properties will this real number assume? Well, part 2 is, or reason number 2, is the resulting product will assume the properties of the non-terminating non-repeating set of real numbers. So it's going to assume the properties of the non-terminating, non-repeating set of real numbers, meaning it's going to assume the properties of irrational numbers. And once we consider why this might be, if we were to, or when we think about attempting to multiply a number that terminates or repeats, and in this case, we will work with the 6.25. If we look at that 0.25 portion and we attempt to multiply that by something that does not terminate and does not repeat, there is not a method, or there is not a way that we can cause this portion that I've highlighted in yellow, for example, in pi, there is not a way that we can cause that to terminate or repeat using a decimal that is being multiplied with that either terminates or repeats. So let me rephrase that. So using a number or a rational number that terminates or repeats, such as 6.25, there is not a way for us to cause the non-terminating, non-repeating portion of an irrational number, such as the yellow highlighted portion of pi in decimal form. There is not a way for us to cause that to be truncated or changed to become either terminating or repeating. And so the properties of the non-terminating, non-repeating portion of the decimal of an irrational number carry over and carry through to the resulting product, which results in an irrational number. So when a rational and an irrational number are multiplied, the result is contained within the set of all real numbers and assumes the properties of the irrational set of numbers.